Good morning, everyone. Welcome to Smart Teaching Online. That has been sponsored by Department of Education, VT Africa Holdings, Fibertech, Distributors, and Vastratech. In order for you to be part of today's assessment, you have to log in to www.hellosmart.com. Sign up as a guest, type in your class ID, which is 59875, and add your name. Okay, we're still carrying on with the consecutive forces. Last time I gave you the difference between the conservative forces and non-conservative forces. Okay, let me just recap on what we did last time. Okay, conservative forces. These are the forces that do not remove mechanical energy in the system. These are the forces that do not remove mechanical energy in the system. What about non-conservative forces? These non-conservative forces, these are the forces that remove mechanical energy in the system. Okay, we discussed about conservative forces. We discussed about non-conservative forces last time. I said when it comes to conservative forces, it follows the path from the start to the end. In other words, the work done by conservative forces is equals to 0, and mechanical energy is conserved. Don't forget that. I gave you an example of gravitational force is the only one that I showed you that is going to play a part on the conservative force. When it comes to non-conservative, I said these ones, they remove the mechanical energy in the system. By saying that, we look at the examples. They are not these ones, these non-conservative forces. They don't follow the conservation of energy. In other words, these non-conservative forces, we have negative work done. How do you get this negative work done from non-conservative forces? We have to look at the friction. It's always opposing the motion. It's always opposing the motion. If it's going to the right, the friction is going to the left all the time. Don't forget, we try to show that during the definition of work and work energy. If you can just look at that, today we are going to look at the work done by non-conservative forces. Okay, if you can just look at this non-conservative force, we have to go back a bit to work energy theorem. Is where it starts. We know that double net is equals to the change in kinetic energy. This time, because we're talking about mechanical energy, we have to think about the gravitational potential energy and kinetic energy. These two, they're going to be aided to give us the non-conservative forces. Okay. All right. The work done by a non-conservative forces is represented by capital letter W, sub of NC, N for non, C for conservative. Okay, don't forget that wherever you see at the formula sheet in your exam, you must look for WNC. If they can say calculate the work done by non-conservative forces, you must note that they're talking about W, capital letter W, sub of NC. Okay. The mechanical energy of an object is not conserved when non-conservative forces are present in the system. Okay, in other words, during the motion, some of the energy is going to be removed. Remember, you can't destroy the energy. You can't create, in other words, it's going to be transformed from one form to another. During the motion, because of the friction, we are going to lose some of the energies in the system. It's either to heat or sound or light. Okay, if we can just look at, these are the examples. These are the examples of non-conservative forces. We have friction, we have a resistance, we have applied forces, we have tension. This is very, very much important. Don't forget this, because in the exam, they can just give you a crate, they can just give you an object just moving upward and downward. So you have to think about if they can talk about friction. If it's frictionless, you must know that the W there, if it's friction and it goes back where it started, or it goes back to the same position, you must know that you must know that it's conservative forces. If it's not going back to the original position, you must know that is non-conservative forces. Don't forget that. These are the non-conservative forces examples. We have friction, we have air resistance, we have applied forces and tension. Okay, we have done all of these in grade 11. So this is just trying to emphasize things that you can come across with. All right, the work done by the non-conservative forces is equal to the change in the mechanical energy of the system. In other words, if you can just look at this, is equals to the change in the mechanical energy of the system. All right, if you can just look at this formula here, we have W, capital letter W, sub of NC, which is equals to change in EK. We all know that change in capital letter E, sub of K is kinetic energy, change in kinetic energy, plus the change in potential energy. In other words, these two here, let me show you. These two here, this is mechanical energy. This is mechanical energy. Mechanical energy is the sum of kinetic and potential. Kinetic and potential. Don't forget that, because that is why now we have to say, according to the definition of work done by non-conservative, that is equal to the change. The change that we're talking about, that is the kinetic energy. From the start, we have initial and final. All the time, that is why we have a change in EK. If same applies to potential energy, we have initial and final. By change there, the final is going to minus initial. In other words, you have to subtract all the time in order to get the change in EK and change in EP. All right, don't forget this. This is very, very much important. And then let me try to emphasize something here. By the change, is what I was saying. By the change here, you are going to have what? This is the change in EKI initial plus EPI initial. In other words, each and every point, we are going to have initial of kinetic energy and initial of potential energy. Same applies, which is equals to, same applies to the final point. It's where you can find the final kinetic energy and final potential energy. Okay, the work done by all the non-conservative forces equal to the change in the total mechanical energy of the system. In other words, we are going to look at these two that I highlighted them. I said we are going to have what? We have to look at the kinetic energy and potential energy. The mechanical energy of an object is conserved. We know that if it's conserved, we are going to have what? We are going to have only the conservative forces present in the system. If mechanical energy is conserved, in other words, the system is not going to lose any. You are not going to lose any energy. You are going to remain with the energy that you have started with. Okay, that is why it's conserved. That is, mechanical energy of a system is conserved when only conservative forces are present. So I need you to bear this in mind. When we have mechanical energy, you must know that we have conservative forces. And then the examples, like I said, example there is gravitational force. I try to explain this under conservative forces. If there are no non-conservative forces present, and then we have W sub of NC is equals to 0. In other words, the work done by the non-conservative forces is equals to 0. Okay, don't forget this. This is very, very much important. Here I try to explain earlier each and every point we are going to come across with the initial of kinetic energy and the initial of potential energy. If you add them up, you're going to get the mechanical, whether is horizontal or is vertical. We are going to have initial and final of these energies, kinetic energy and potential energy. All right. In other words, during the conservative forces, we know that the initial kinetic energy plus the initial potential energy is equals to the final kinetic energy plus the final potential energy. In other words, we don't have any change at all, which is equals to WNC equals to 0. Don't forget that under conservative forces. They can say during the motion, we are not going to have any non-conservative forces. You must think about, okay, if we don't have non-conservative force, we have only gravitational force that is acting on that particular object, and then the motion will rotate around. If it's a loop, it will just move around, starting point, moving around, and up at the same point where it has started. And then work is equals to 0. Remember, the definition of work is the product of the force. In other words, it covered nothing. Thank you. Okay, that's mechanical energy is conserved when they are non-conservative forces. All right. Let us look at this. Let us look at this. I need you all to pay attention on this one because this is very, very much important. Okay, it's either starting from up to down or down upwards, or it's horizontal. It doesn't matter as long as you can just analyze the information. I told you that when you come across with this, you write down the given information. After that is where you can start with whatever that they need you to calculate. Okay, let us look at it. In a factory, small packages, each weighing this 4.5, each weighing 4.5. Okay, travel on a conveyor up to the point of completion. One section of the conveyor belt is slanted at 30 degrees. At 30 degrees. I'm trying to highlight the given information so that it will be easy for us to write our data. Okay, it's slanted at 30 degrees to the horizontal. Okay, if we can just look at the diagram here, we have 30 degrees here, we have H here with asymptotic line or a broken line that is height, and then we have this inclined. In other words, it's moving from here up to here. We have point A and point B. On this, in this journey, we have this change in angle. Look at the distance from A to B. We have 4.5 meters. Okay, a package travels up the conveyor belt with an initial in other words, we have been given the initial velocity. That is the initial speed. The moment you see initial speed, you must know that this is our initial velocity. Okay, this is the velocity of 2.5 meters per second. Okay, the package package reaches the top of the conveyor belt at a speed of 0.5 meters per second. This is your final velocity. This is your final velocity. Started here with 2.5. Your final there is 0.5 meters per second. In other words, the final velocity is equals to 0.5. What are they looking for? Calculate the work done by the non-conservative. By non-conservative. Present. Okay. They told us this is non-conservative forces. In other words, we have to expect the friction. Obviously, we have to think about friction here. All right. Let me extend the page so that we can have enough space. Let me extend the page. What I'm going to do now, I'm going to write down the data of this given information. This is the data. Let me take this pen. Data. We have this data. What is it given? We have a mass of each is equals to 4.5 kilogram. And what else? We have theta there. Theta is equals to 30 degrees is what we have been given. And then what else? Initial speed, initial velocity. We have 2.5 meters per second. 2.5 meters per second. And the other one is final velocity, which is 0.5 here. 0.5 in meters per second. And what else? Calculate the work done by the non-conservative forces present. Okay. We have been given something else again. What is that? From the diagram there we have a distance covered. The distance covered there, I can just say change in x, which is equals to 4.5 in meters. What are they looking for? Okay, work done by non-conservative forces. I said we have to look at the W, capital letter W, sub of NC, which is equals to the change in kinetic energy plus the change in potential energy. In other words, that is a change of total mechanical energy of the system. All right, let us carry on. What do we have? We have been given this. What about the height? In order for us to calculate the potential energy, we don't have. If we can just look at this, I need you to look at this diagram. I need you to look at this. Okay, we have our H here. Our H is unknown. Your H is unknown. What about this? Is the opposite side. This is adjacent. This is AD. This is OP. This is HY. Hypotenuse. If we can just look at that, we have adjacent, we have opposite, we have hypotenuse. You have to go back to mathematics and trigonometry. We have adjacent here, we have opposite, we have hypotenuse. Okay, hypotenuse there is given. If we can just look at them, we have what? We have 4.5. All right. Now, first and foremost, we have to calculate the h. Let us calculate the height. How do you get it? How do you get it? Let us go back to the diagram. We all know that sine theta is equal to opposite over hypotenuse. Opposite over hypotenuse. Okay. If we can just look at that, if it's adjacent that we were looking for, we're just going to say cos theta is equal to adjacent over hypotenuse. But now we are looking for h. H is on the y-axis. All right. We have to say sine theta is equal to opposite over hypotenuse, which is equal to opposite is h, and then hypotenuse is 4.5. Is 4.5? Is 4.5? Okay. Now we have to say sine 30 degrees. Sine 30 degrees, let us check. It's 30 degrees, which is equal to opposite over hypotenuse, and the hypotenuse there is 4.5. The opposite is all right. Let us make h to be the subject of the okay. Then h is equal to 4.5 30 degrees, which is equal to, extend the page. Let me extend the. Hopefully you have your own calculator. I need you to take it out and work out this h. Okay. 5 multiplied by, that is sine 30 degrees, which is 2.25 in what? In meters. That is the height. Okay, the moment you have h, you can calculate. It's gonna be easy for you to calculate the potential energy. The potential energy. Okay, let us start with the change. To extend, let us start with the change. Let us start with the change in kinetic. We know that the change in kinetic energy is equals to half mv final squared minus half v initial squared. Okay. If we have this, I have to say it's equals to. Let us substitute. Let us go back and check the given information. Your mass there is equals to what? Our mass is 4.5. Our mass is 4.5. It's half multiplied by 4.5 multiplied by the final velocity. The final velocity there is 0.5. It's 0.5 squared. Don't forget that because it's very, very much important. Which is equals, this is minus, not equals, minus half 4.5 multiplied by the initial velocity. Let us go back and check initial velocity is 2.5. Initial velocity is 2.5 squared. Okay, let me extend it. Let me extend it. Hopefully we are still together up to here, because what I was just doing, I went back to the given information. I just take them and just replace them as they are. Okay, now I have to say is equals to, let us use our calculators. Let us use our calculators. Let us use our calculators. Okay. That is half multiply by 4.5 multiply by 0.5 squared is 0.5625 minus, you have to say half multiply by 4.5 multiply by square root of 2.5. Okay, let me just verify that. Multiply by 4.5 multiply by 2.5 squared, which is 14.062. Zero 6 2 5 0 6 2 5 0 6 2 5. I don't know what is happening, but anyway, this is 6. This is, let me erase this. 0 6 2 5. It's okay, because it doesn't want to change. Fine. So I didn't choose that pen, which is equals to which is equals to let us check. That is half multiplied by 4.5 multiplied by 0.5 squared, which is 0.5625 minus 4.0625. Okay. Hopefully you get is minus I don't know what is happening. It's minus 13.5 joules. Okay, this is the change in kinetic energy. Let me extend the page and calculate the change in potential energy. That is change in potential energy, which is equal to mg h final minus mg h initial, which is equals to, if you can just look at that, we have the same mass, in kilograms multiplied by, let me extend the page. I'm just substituting the values. G there is gravitational acceleration, which is approximately 9.8. It's 9 meters per second squared multiplied by your final 2.25 meters. It's 2.25 to 1. Okay. That is final. Minus the same mass of 4.5 multiplied by 9.8 multiplied by, that is 0. Okay. In order for you to understand this, you can say the final, your final here. When I'm saying final is 2 point, is at B, is where you can find what? You can say final, my final height is represented by HB, H sub of B. My initial height is going to be represented by H sub of capital letter A. If you are lost here, you can just say if your final here is B, your initial there is A. Okay, same applies to kinetic energy. You can say this final is B, this one is A. So the same. Okay. Which is equals to, let me extend the page. I need you to use your calculator. Let us use the calculator. And then we have 4.5 multiplied by 9.8 multiplied by 2.25. That is 9.225. Okay. The other one, we can just calculate it, because anything that is going to be multiplied by 0 is 0. Let me just here, and then I can say, let us go back. Let us go back to the formula of work done by non-conservative forces. We have to W sub of NC, which is equals to the change in EK plus the change in EP. Okay. Let us look at the change. We have calculated the change in EK. Change in EK is minus 13.5. Minus 13.5. These are in joules. Let me not include. Plus the change in EP. The change in EP is 999.225. Okay, if we can just look at that, all of them, they are in joules, which is equals to, okay, 99.225 minus 13.5, which is 85.7. 85 point, let me say 86 because it's 85.7. 85.7, I can say is 80. It's 86 joules. Okay, this is your answer. Okay, now we have we have to look at the following as well. Let us look at this. Another example here. Another example. What I need you to do, I need you to be ready. If you are taking notes, you have to do that quickly. I need you to be quick so that we can finish this. All right. Let us start with this example. A roller coaster with a combined mass of 3,000 kilograms. If you can just look at this, this is the mass of the combined roller coaster, which is 3,000 kilograms. There's a speed. In other words, we have this initial. There's a speed of 13 meters per second. 13 meters per second. As it goes over a 20-meter hill, we have been given also the height. This is your height, as indicated on this diagram. We have A here and this height here. The height that we have is 20 meters. Now let us carry on and check here. We have, go back to highlighters. Upon reaching the crest of the 9-meter hill, in other words, is from A to B. This is your crest there. We have this height that is given there. We also have this speed. Upon reaching the crest of the 9-meter hill, it's right there on the right hand side, its speed has increased. The word increased, in other words, we have started somewhere, now we have changed. In other words, your final velocity is 17 meters per second. Okay, at point A, we have initial velocity of 13 meters. At point A, we have the mass of 3,000. Okay. At point B, we have a height of 30. We have the mass of 3,000. We have the velocity of 17 meters per second. Okay. Calculate the work done by friction on the roller coaster. In other words, the moment you see this, it's non-conservative force that is always opposing the motion. All right, let me extend the page so that we can work on this. All right. I told you earlier that all the time you have to write down the given information as a data. This is very, very much important. It's going to help you. Can't do mistakes. Okay, your mass there was to 3,000 in kilograms. All right. And what else? That is the mass of the roller at A and at B. All right. What about the other given information? We have velocity. I will write like this. I said the VA is equal to 30 meters per second. You can say V initial or V at point A. Okay, and what else? We have H. In other words, that is the height. Where? At which is equal to 20. Which is equal to 20 meters. Okay. Let me extend the page. If we have that, what else? Upon reaching the crest of the 9-meter, we have been given another height. That is H of which is equals to 9 meters. That is our height at point B. And then we have been given also the speed at B. In other words, that is velocity at B. That is the final velocity. Don't be confused by these letters. Stands for final velocity, which is equals to, what is that? At B, we have to look at it. That is 17 meters per second. 17 meters per second. Okay. If we have that, and what else? And what else? That's all. We are looking for what? W and C. Is all. Let us do it like this. You have to say W and C is equals to the half mv at B. That is the final, which is squared, minus. Remember, according to the formula of non-conservative, we have W and C equals to the change in kinetic energy plus the potential energy. In other words, let me start with the kinetic energy here. I will just show you that as well. That is minus mVA squared. All right. Plus, remember, this is the mechanical energy of the system. We have to add. That is the total of mechanical energy. In other words, we are going to have what? That is the, for gravitational potential energy, we have the mgh. For mgh, mgh of B minus mg h of A. Okay. This is the sum. This is the total of mechanical energy. We have kinetic energy and gravitational potential energy. All right. As you can see there, we just carry on. We can say, let us start with the value we have. Let me say half. The mass there is 3,000 to 3. Then velocity at B. Velocity at B is 17. That is 17 meters per second squared. Don't forget that. Minus. We're still up there in the kinetic. We're still up there in kinetic energy. I need you to follow me. 3,000. The initial velocity. The initial velocity. Okay. The initial velocity there, it's not like clear, but anyway, initial velocity is given. Initial velocity, where are you? Okay, 13 meters per second. 13 squared. Okay. This is our change in kinetic energy. We have to say plus. Or let me just put it. This is plus. Plus what? The change potential energy, which is the mass there is 3,000. 3,000. Let me say open bracket 3,000. Your G there is 9.8 multiplied by the HB. Where are you? Where are you? It's 9, which is 9, which is minus 3,000. 1, 2, 3. 3,000 multiplied by Let me try to. All right. Okay. That is 3,000. 3,000. 3,000 multiplied by h, which is 9.8. Multiply by 9.8. Multiply by 0. At A, is it 0? No, it's not 0, it's 20. At A there is 20. It's 20. It's 20. That is the height at A. Okay, this is very, very much important. You have to keep on checking. Keep on checking whether you are substituting the right thing or not. Okay, which is equals to, let us look at it. I need you to use your calculator. I need you to use your calculator. I need you to use your calculator. By 2 multiplied by 3,000 multiplied by 17, which is squared, which is 433,500 minus. I can just say that's 1 divided by 2 multiplied by 3,000 multiplied by 13 squared, which is 253,500. Okay, I can just close it, plus for the gravitational potential energy. I can say 3,000 multiplied by 9.8 multiplied by 9, which is equals to, let me just open. I'm trying to do part by part so that you can see what I'm doing. Okay, if 2,646 minus, that is 3,000 multiplied by 9.8 multiplied by 20, which is 508,000. Okay. This is your change in gravitational potential. Let us carry on with the calculations. 433,500 2,535,000, which is 180,000 of the change in kinetic energy, plus, so we put plus, I say plus, 2,600 minus 588. This is plus, minus 323. Okay. Plus 180,000. That is minus 143,400. Okay. All right. If you can just look at this. If you can just look at this, this is the work done by friction. You're not supposed to write it like this. You can leave it like this. or you can just say this is approximately 143,400 joules. Thank you for today. See you tomorrow. We're just going to finish this. Bye.